Hi there, welcome to your very first lesson on a really important chemistry concept called the mole. And you might have no idea what a mole is, but you might have heard that chemists celebrate something called Mole Day. And you might be wondering what that's about. So, Mole Day is actually a day celebrated every year on October 23rd, and technically it starts at 6:02 in the morning. So you still might not understand what that means. A mole in chemistry is actually a certain number, and that number is 6.02 times 10 to the 23rd. Okay? It's basically a giant number that has a very particular meaning, so that's what we're going to be getting into today, and we're going to learn how to work with that number. But you might now see why we celebrate on 6:02 in the morning on October 23rd, because that is the day and time that corresponds to Avogadro's number, which is that number. All right, so what the heck is mole? The definition is a mole is the amount of substance that contains the same number of atoms as 12 grams of carbon 12. So what I want you to focus on is that it's a counting unit, and it's very much like a dozen. So a dozen is 12 somethings. It could be anything. It could be a dozen donuts. It could be a dozen pencils. It could be a dozen people. It's 12 of whatever it is you're talking about, okay? A couple is two somethings. A couple of people is two people. A couple of pencils is two pencils. A couple is always two. So a mole is also always a certain number. It's always 6.02 times 10 to the 23rd things. Now, again, what you really just need to comprehend is that as a gigantic number. So it's 602 with 21 zeros after it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So this gigantic number right here is a mole. And again, that could be anything. It's the same number of things as there are atoms in 12 grams of carbon 12. Okay? So that number was discovered by a scientist named Amadeo Avogadro, and so he gets credit, and we call it Avogadro's number. And again, the big deal is this is like the big chemistry deal, okay? What do we care about? 1 mole of any element has a mass in grams equal to its average atomic mass. So again, if you go back and look at our definition, it tells us that it's the same number of atoms as 12 grams of carbon 12. So it's 12 grams, and that corresponds to the 12 AMUs of carbon 12. Okay, so that's a certain number of atoms. Well, if you have a different isotope, so let's say that you have nitrogen. Okay, nitrogen's average atomic mass is 14.01 AMUs. Okay, that corresponds to 14.01 grams if you have 1 mole of nitrogen. Okay, so 1 mole of nitrogen atoms would be 14.01 grams. So we're going to try some practice here. This might not fully make sense right now, but hopefully with a couple of examples it will start to make sense. So if I tell you that 1 mole of helium has a mass of 4 grams, you might wonder, how do you know that? Where did that number come from? So we look at the periodic table, and if we look at helium, we see that its average atomic mass is 4.00. That's the decimal number, okay? So helium's average atomic mass is 4, so if you have 1 mole of helium, it's 4 grams. Well, how many atoms is that? Because we know that it was 1 mole, we know that it is 6.02 times 10 to the 23rd atoms. Okay, that's always the answer if you have 1 mole of something. Okay, so our next question to think about, 1 mole of sodium is 22.99 grams. Again, where did that number come from? 22.99 grams. It's the same number as the average atomic mass of sodium. So sodium, its average atomic mass is 22.99, that's AMU. But when you have 1 mole of it, it's 22.99 grams. So 1 mole of sodium is 22.99 grams. How many atoms is that? Well, just think about how many moles it was. It was 1 mole. So it is 6.02 times 10 to the 23rd atoms. Okay? So we really have 3 things that are equal here. 1 mole of an element equals 6.02 times 10 to the 23rd atoms. And that also equals, I'm going to abbreviate AAM, its average atomic mass in grams. Okay, so really those three things are all equal. Here's another example. 1 mole of oxygen has a mass of 16 grams. So you should know that that 16 grams is the average atomic mass of oxygen. If you have a mole, which is a gigantic amount, it's grams. And again, how many atoms is that? Well, it's 1 mole. So 6.02 times 10 to the 23rd atoms. I'm not going to ask you any more of those, okay? If it's 1 mole, it's 6.02 times 10 to the 23rd. We already did that one, so we'll skip that. All right, here's one. 1 mole of potassium has a mass of how many grams? Okay, well, 1 mole of an element equals its average atomic mass number in grams. So we'll go to our periodic table and find potassium, which is K. So its average atomic mass is 39.10 AMUs. So its mass, if you have 1 mole, is that same number, 39.10 grams. Here's another one. Neon, 1 mole is 20.18 grams. That's its average atomic mass. How many atoms is that? Well, I'm just going to write Avogadro's number, 6.02 times 10 to the 23rd. I don't know why this same question keeps popping up. Getting some repeats here. Here's some different examples to think about, okay? 1 mole of oxygen, like actual oxygen gas, has a mass of 32 grams. Now, if we look at the periodic table, that doesn't match. Oxygen on the periodic table says 16, but I'm telling you, 1 mole of oxygen gas has a molar mass of 32 grams, a mass of 32 grams. 1 mole of nitrogen has a mass of 28 grams, okay? Again, go to the periodic table. Nitrogen should be 14, and I'm telling you it's 28. 1 mole of hydrogen has a mass of 2 grams. Hydrogen should be 1, but I'm telling you it's 2. 1 mole of fluorine has a mass of 38. You can probably guess what we're going to see when we go to the periodic table. Fluorine has a molar mass of 19, an average atomic mass of 19. But I'm telling you, 1 mole of fluorine has a mass of 38 grams. So why are these elements here when we have 1 mole of it? Its mass is actually the average atomic mass times 2. What's going on here? Okay. This is a phenomenon called diatomic elements. And you talked about one of these in biology. Okay. These elements here always exist as pairs unless otherwise stated. Okay. So the one that you might remember from biology is oxygen. When you wrote chemical equations involving oxygen, like maybe cellular respiration or photosynthesis, you never wrote O, you always wrote O2. So whenever we write these elements, we write them as pairs. So O2 actually means 2 oxygens bonded together. F2 means 2 fluorines bonded together. Cl2 is 2 chlorines bonded together. So this is just kind of a fact that you need to know about these 7 elements. And I'm kind of weird. I like to come up with weird words to help me remember things. So my high school chemistry teacher told me if you take these 7 elements and you just pronounce them as you see them, it's Hernafkelbrei. So these are technically called the diatomic elements, but I sometimes say that they are the Hernafkelbrei elements, and that's just my weird kind of mnemonic device to help me remember it. So anytime you see one of these elements for the rest of your time in a chemistry class, you're always going to write them with a subscript of 2 unless something else tells you otherwise. So this concept that we've been introducing is called the molar mass, okay? The molar mass is literally the mass of 1 mole, okay? The mass of 1 mole. And what we've been seeing is that if we have 1 mole of a substance, its mass is equal to its average atomic mass measured in grams, okay? So we take that number, the average atomic mass from the periodic table, and put a grams after it. So what's the molar mass of helium? It's going to be whatever its average atomic mass is in grams. So for helium on the periodic table, its average atomic mass is 4. So its molar mass is also 4, but it's 4 grams. Okay? Because a mole is a really big number, that's a lot of atoms. It's so big that it can actually be measured in grams now. So 4 grams. Okay, molar mass of iron. So same thing. We're going to take the average atomic mass of iron, but we're going to put grams behind it. Okay, so iron is Fe. So right there, 55.85. So 55.85. We call this the molar mass of iron. Next, calcium. We want to know the average atomic mass of calcium. So we go to the periodic table, we find it, it's 40.08. But notice what this question's asking. This one is actually, we've switched gears. This said average atomic mass. That's just the number from the periodic table, and it's not the molar mass. So that one's actually AMUs. It's kind of tricky here. Okay, it's 40.08 AMUs. Now this question's different and asks for molar mass. So molar mass is the one that we refer to in grams. So if we're talking about a single atom, atomic mass, it's very small, and it's that atomic mass unit, AMU. If we're talking about the molar mass, that's the big, gigantic amount of atoms, and we measure that in grams. Okay? Again, here are the 3 things that are equal to each other. These can be used as conversion factors. 1 mole of anything equals 6.02 times 10 to the 23rd atoms of that element. And that also equals the molar mass in grams of that element. Okay, so if I were to pick an example, let's take the element neon, Ne. Okay, I could say that 1 mole of neon equals 6.02 times 10 to the 23rd atoms of neon. And that also equals the molar mass of neon in grams. And I got to go look up that number. Neon is over here, 20.18. So 20.18. So for any element, you can come up with these 3 things that are equal to each other. Okay? To do a problem with moles, you're probably going to start out doing conversion problems where you, let's just look at an example. How many atoms are there in 55.4 grams of lithium? You're going to follow the same steps as dimensional analysis. So you start by putting the number that you know over 1. So you put some number over 1. You do a little conversion. You bring that, if that's grams, you bring that unit down. You put the unit that you want on top, maybe atoms, and then you fill in the numbers. So remember, whatever numbers you plug in to this conversion right here, they have to be equal numbers. So an equal number of atoms and grams. So you use these equal things. So if it's a mole, you put a 1 in front of it. If it's atoms, you put Avogadro's number in front of it. And if it's grams, you put the molar mass in front of it. Okay? So again, this number here, I can't stress this enough. This number here is what you were given. What are you trying to convert? It's these numbers over here in the ratio where you're going to plug in these things. If it's a mole, you put a 1 in front of it. If it's atoms, you put 6.02 times 10 to the 23rd in front of it. And if it's molar mass, if it's grams, you put the molar mass of that element in front of it. Okay, so let's walk through this example together. If the question is how many atoms are there in 55.4 grams of lithium, so here we begin by putting what we know over 1, 55.4 grams of lithium. We know that we're going to do a conversion, so we draw our line for our ratio. We bring down the unit, grams of lithium, and we put the unit that we want on top, atoms. And then we plug in our numbers. Again, this ratio here is where we plug in those equal numbers, either 1 mole or 6.02 times 10 to the 23rd atoms, or molar mass, which is the decimal number on the periodic table, goes in front of grams. So this top number here is going to be Avogadro's number, the big number, and this bottom number down here is grams, so we're going to use the molar mass of that element, lithium. So there's our Avogadro's number on top and the molar mass on bottom. If you wonder where that 6.94 came from, remember it's from the periodic table. Lithium, molar mass, 6.94. So next you cross out your units. The unit left over is atoms of lithium, so that's the unit of our answer. And we have this big long number, 4.80559, keeps going, times 10 to the 24th atoms, okay? And hopefully by now you know that you can't give a big long answer like that, so we need to round to the right number of sig figs. So however many sig figs there were in your measurement, ended up right there. That's really what determines your answer, because these things over here are not measurements. These numbers right here are considered to be exact, so the only measurement is this one right here. So since this had 3 sig figs, we want to round this answer to 3 sig figs, so 1, 2, 3, and it becomes 4.81 times 10 to the 24 atoms of lithium. So that is a lot of atoms. That's kind of the concept here, is that if you have a mass that's big enough to, be a significant amount and be observed, it's going to be a lot of atoms. So I'm going to walk you through a couple more examples right now with no narration. We're just going to speed through the examples that you have in your notes. Keep in mind that these examples that we're looking at are just following these rules that you basically are doing dimensional analysis. You put what you know over 1, you bring that unit down, you put the unit that you want on top, and you fill in the numbers. And remember, these are always the numbers that you fill in. So we're going to speed through some examples. Here we go. hope those examples were helpful. The mole is a very important concept that you're going to continue to use for the rest of the year in chemistry. So if you have any questions, please don't hesitate to ask your teacher, and they would be happy to help you because the mole is a very useful concept that you're going to continue to use, so you need to make sure you understand it now. Thanks again for watching.